All right, good morning, my chemistry students. To help you guys study for your test, I'm going to make you guys a couple videos on Unit 7. Let's start with 7.1 Stoichiometry, Part 1. I broke up stoichiometry for you guys into 3 separate lessons. The entire unit technically is on stoichiometry, but to really introduce you guys to stoichiometry, I separated it into 3 lessons to kind of try to do it a little step by step for you guys. So by 7.3, we're going to do a full stoichiometry problem. But 7.1, 7.2, 7.3, I'm just adding on a little bit each time. And so 7.1, what I taught you guys was just one thing, which was the mole ratio. The mole ratio really is the central key. It's the principle behind all of stoichiometry. And so I wanted to make sure that you guys really understood it well. And to help you guys understand it, this abstract concept, I use this analogy of sandwich making. And so let's take a look at that before we take a look at any real chemistry. Hopefully it'll help us understand it. And so, because you guys know how to make sandwiches. You guys do it all the time. So let's say, for example, we're trying to make a cheese sandwich, a very simple sandwich consisting simply of 2 pieces of bread and 1 piece of cheese. How can we kind of represent that? Well, we can write it out like this. We can say, if I have 2 pieces of bread and 1 piece of cheese, if I combine those together, I can form 1 sandwich. Right? And that makes sense to us. And in this situation, we're combining things, right? We're combining them in a specific ratio. Now, this is kind of a lot to write, so let me maybe rewrite this with symbol. Let's use B for bread, okay? So I'm going to say, hey, 2 B's, and then for cheese, let's write C, okay? So 2 B's and 1 C, that's going to equal, it's going to yield, so let's use the arrow for that. That's going to yield 1 S. Now I realize actually I put an arrow here too, so let me remove that so you guys don't get confused. That's like a bullet point, that arrow. So 2 breads and 1 cheese make 1 sandwich, right? And so what's happening here basically is that in order to make 1 sandwich, we're using 2 breads and 1 cheese. So for every 1 sandwich, we use 2 pieces of bread. It's 2 pieces of bread per 1 sandwich. So we can write that. We can say, hey, it's 2 pieces of bread per 1 sandwich. And that's true, right? Yeah, for every 1 sandwich we make, we need to use 2 pieces of bread. Another way to write this is what we call a ratio. And another way to write a ratio is you could write it as like this with a colon in between. Or another way that you could write a ratio is kind of as a fraction. And so you could write 2 B's per every 1 S, this little fraction line, that means per. And so these are all different ways of writing ratios. These are all ways of writing ratios. Now, that's one of the ratios that's present here, 2 breads per 1 sandwich, but another ratio is 1 cheese per 1 sandwich, right? And so that's another thing that we could say. We could say, hey, for every 1 sandwich, we need 1 piece of cheese, 1 cheese per 1 sandwich, 1 cheese per 1 sandwich, or again, we could write it like this, right? And so these are ratios in our everyday life and things that you know in cooking and baking, right? You guys know ratios, that they show the quantitative relationship between ingredients, between things, right? And so we understand that. Now, we're going to apply this idea of ratios to making something else, to making chemicals, to making molecules, which is what chemistry is all about. It's about chemical making. So let's say we're trying to make iron oxide, Fe2O3, which looks something like this. So if we're trying to make Fe2O3, we need to combine things, right? In the same way that in baking and in cooking, we combine things to make new things, we're going to do the same thing in chemistry. And it turns out this is the recipe for making iron oxide. What you need to do to make iron oxide is you need to have 4 irons, Fe, and 3 carbon dioxides, CO2, and that is going to equal 2 iron oxides, 2 Fe2O3s, as well as 3 carbons are going to be produced in that situation. And so we can rewrite this just like above, or with the sandwich making in terms of symbols. We can just write it as 4Fe plus 3CO2 yields, it produces 2Fe2O3 plus 3 carbon. And so similarly to sandwich making, right? What we can see here are ratios. We can see that in order to make 2 Fe2O3s, you need to have 4 Fe's. In other words, 4 Fe's per every 2 Fe2O3s. In order to make 2 Fe2O3s, we need to have 4 Fe's, right? We can rewrite that, write that another way as 4 Fe per every 2 Fe2O3, or 4 Fe per every 2 Fe2O3, like this. Again, remembering that this means per. And so what we have here, right, again, these are all just ratios. They tell us the quantity in which things are combining here in order to make stuff. Now, we call these ratios, but actually we go one step further. These are what we call mole ratios. And mole ratios, simply put, they are what tell us, they relate to us, the number of molecules of one substance in an equation to the molecules of another substance. Now, here's the tricky thing with the mole ratio. Some people think that, oh, wait, so moles means molecules? Not quite, right? Remember that the way that we go from molecules, or sorry, from moles to molecules is we just multiply by 6.022 times 10 to the 23. But here's the thing, if I did that, right, if I multiplied this and this by 6.022 times 10 to the 23, we have the same thing still, right? So just, if you care to know why we call it mole ratio rather than molecular ratio, here's just an aside. Right, if I have, for example, 1/2, and I multiply both sides by 2, what would I get? Right, we get 2/4. Now, is that ratio, are these ratios any different? Is 1/2 any different than 2/4? No, right? They're the same thing, right? This simplified becomes this, right? So if we simplify this, it becomes this, right? And if we scale this up, it becomes this. They're the same ratio, right? So if you multiply both things by the same thing, you're gonna get you're gonna have the same ratio still, right? So if I took this, and this is really, we're talking, I guess, atoms here and molecules here. If I wanted to turn this into moles, right, what I would do is I guess I would divide both sides by 6.022 times 10 to the 23, right? But do you see that I'm doing basically the same thing? Here I multiplied both by 2. Here I'm dividing both by 6.022 times 10 to the 23. But so really, right, like, this didn't really matter because we did the same thing. It canceled each other out. And so similar thing here. If we're doing the same thing, we're canceling each other out. And so, if we're going from here from atoms and molecules to moles, we'd have the same thing. So the mole ratio is the molecule ratio or atom ratio, right? So anyways, that's just an aside for you guys. If some people ask me, why is it called the mole ratio? We're talking about molecules and atoms. So that's why, right? There's the same thing. So anyways, if you really don't care about that, whatever, just go with this definition then. What the mole ratio is it relates number of molecules or atoms of one substance in an equation to molecules or atoms of another substance. And we derive this from the coefficients of the substances in a balanced chemical equation. Okay. Now I do want to emphasize balanced, okay? So your chemical equation has to be balanced. Once it is, just take the coefficients, okay? Remember, the coefficients are the big numbers in front of our substances, in front of our symbols, right? And so, for example, here, right, these were all what we call coefficients. Do not look at these, not the blue things I circled, right? Those are what we call subscripts, okay? So don't look at the subscripts, look at the coefficients. And so let's take a look at some examples. So taking a look at this same equation, 3 example problems, right? What is the mole ratio between Fe2O3 and Fe? Well, as we just did, right? What we have to do for that is take a look at the coefficients. And so it's 2 Fe2O3s per every 4 Fes, right? You could write it like this, or you could write it like this. Or, and here's another thing, right? Like you could write it like this, right? There's no difference between these two things. You could reverse the order, it doesn't really matter. You could also say, hey, 4 Fes per 2 Fe2O3s. That would also be valid, just kind of writing it out verbally. So all of these are mole ratios. And we get it from the coefficients of the balanced chemical equation. And so here, it's 2 Fe2O3s per every 3 CO2s, right? And so I'm just going to write it one way now to save you guys time, but you guys can see that you could write it in a variety of ways. I'm going to write it this way, though, because this is how we're going to be using it in stoichiometry, right? So we're going to be using fractional ratios. And so that's the answer to that one. And now here, for Fe2O3 to C, 2 Fe2O3s for every 3 Cs. Now, sometimes students say, wait, but they're on the same side. Yeah, it doesn't matter, right? Here, we're still combining things together, right? We're saying, hey, 2 Fe2O3s is going to combine with 3 Cs. 3 Cs are going to combine with 2 Fe2O3s, right? That's the ratio in which they need to combine, right? 2 breads combine with 1 piece of cheese to make 1 sandwich, right? And so the ratio is still valid even if they're on the same side. And so that's mole ratios, right? Long story short, what you really need to worry about, what you really need to care about is the fact that you derived these from the coefficients of substances in a balanced chemical equation. All of this, what I was trying to show you guys, was what we call conceptual understanding, so that you actually understand what you're doing, but this is ultimately how to do it, okay? Derive it from the coefficients of substances in a balanced chemical equation. Well, hopefully that helps, and hopefully the other videos help too. You guys got it. Keep studying hard. Proud of you guys, rooting for you guys. Come by my classroom anytime you need help.